So, thanks a lot, Stephen and Stefan, for inviting me. I'm very happy to be here. I'm presenting a project that was originally designed just for educational purposes, and it turns out to be, after a few years of developing it, it turns out to be a project that is actually also suitable for doing some specific research, and I'm getting to that later, towards the end of the talk. So I should tell you, before I get into this, I should tell you the story about how I got to develop the system. This goes back to 2014, when I was invited to teach a class in the civil engineering department at Berkeley. And I was supposed to actually teach master students in that program computer science basics, right? And in one semester. And I prepared the class and everything, and then I started teaching the class, and I realized within a week that the students, about 20 students in the class, all very smart, very bright Berkeley students, that they had basically no clue of computer science. They were programming, they were developing code every day. Like, this was probably 80% of their time that they spent was actually just coding, like what we do as well. But they were supposed to study civil engineering on top of it. So they didn't have time to do it, and they were very unhappy about it because they were coding and didn't really understand what they were doing. And I asked them, how are you actually doing this? And these people are not just developing, you know, a little numerical function or something that gives you something, a number for an input. They are actually developing system software across hundreds of sensors deployed on a bridge, and then they communicate to your app on a phone, etc. So it's really complicated, sometimes even real-time software. So I asked them, how are they doing this? And they said, Stack Overflow. And Google. So you just Google your problem, you get your whatever answer, you take the snippet of code that you find here and there, and then you put it together without really understanding what's going on, and then you have all these bugs, and you have all these problems, and so on and so forth, right? They're very unhappy about it. By now, people are telling me that, what's the difference to computer science people? Aren't they doing the same thing? That's a different story. So in fact, after doing all of this work, it actually turns out that my teaching in, you know, not just non-CS majors, but my actual computer science students has also improved because of the system. So the idea was to actually develop, and I started doing that in 2014, to develop something that allows me to teach computer science basics all the way from architecture and programming languages and compilers to runtime systems and operating system kernels and hypervisors. And what came out of this idea of trying to explain people the absolute simplest basics of how to get there, how to even, you know, where does the meaning of a programming language actually come from, and how does it translate to the actual hardware that executes it. That Selfie project is the product of this goal, right? And we are still developing the system even after 4 years. You find a lot of material right there. But before I start, I should actually also mention that Selfie is, of course, the name doesn't come from taking a selfie. It actually comes from the notion of self-referentiality. And you'll see that in the talk that there's a lot of self-referentiality in the system on different levels and so on. And actually, one of the fundamental goals is to teach and to make people understand how you resolve the self-referentiality. Okay? Which is a challenge that we should still try and address in teaching classes on computer science basics. On a very high level of abstraction, this is about teaching the construction of semantics, of formalisms, of programming languages and machine code, and even concurrent programs. And we use different techniques to do that. Compilation, interpretation, virtualization, which is particularly difficult to teach so that you actually understand it, especially to engineers. And then lately we are also looking into teaching or including verification techniques, because verification requires you to actually reason and talk about software on different level of abstractions than just programming languages, and that helps you actually understand the whole system again. For example, it's very difficult for students, CS students or non-CS students, to get a formal understanding of how you even reason about the correctness of the code that you're developing. Okay? This is a big project, there's lots of people involved, and just mention them here quickly, mostly students in my group, but also some external people. There's also a lot of inspiration when you actually look at the code in the system, right? Then you'll find that, ah yeah, this must be Niklas Wirth's style of doing a very simple compiler. And this must be Jochen Liedtke, you know, when you design a microkernel, for example. Okay. So before I go further into the details, I will just tell you exactly what it is. So Selfie, and for people who can really read this in the back, Selfie is a self-referential 10,000 line C implementation in a single file, which is called selfie.c. And you can download it from GitHub, okay? And then you just do gcc selfie.c and you have your executable. That's it, okay? It implements a self-compiling compiler, yeah, that compiles a tiny subset of C that I call C star for good reasons, into a tiny subset of RISC-V called RISC-U for unsigned, a very small unsigned subset of RISC-V, which is the latest, let's say, incarnation of MIPS, if you want, in an open source version. What's also important is the language C star. So the whole thing, of course, since it's self-compiling, the whole thing is actually not written in C, but in this tiny subset called C star. Then there's more, which is very important here, and this is some of the unique features of Selfie. There's an implementation of an emulator called Mipster. It used to support MIPS code. Now it executes RISC-U code, right? And since it is implemented in the same file, it can execute itself any number of times, in fact. Yeah? And you might think, well, that's weird. You know, what are you doing with that? You will see that later, that this actually does make sense. There's more. There's a self-hosting hypervisor called Hipster. Okay? Names are important for students. That virtualizes the emulator, exactly the machine emulated by Mipster. And on top of it, this thing can host all of Selfie, including itself, any number of times. Okay? So it's a self-recursive virtual machine. There's more. There's a self-executing symbolic execution engine called Monster, which is truly a monster. It's not finished. So this is a prototype. All this stuff here is nicely done and documented and everything. This is ongoing work, right? So Monster is a thing that actually executes this RISC-U code symbolically. And I thought, I started doing this a year ago. I thought that's an easy thing to do. It's a nightmare. And so, and this is actually the topic, the research part of this project. Okay? There's a bit more. You need a tiny library in there because the whole file is completely self-contained. Okay, so there's no includes, there's no import, there's no libraries. We bootstrap this whole thing from 5 system calls. Okay, and they have to be wrapped in this library, etc. So when you actually read the code, you understand how the whole thing bootstraps from nothing, right? From a processor, essentially, from an architecture. There's also a tiny experimental SAT solver in there called BabySAT. That is something I did because I thought I need a SAT solver for this monster thing. That's not true anymore, so it's just there for if you want to explain someone how SAT solving works on a very basic level. Very important, Selfie supports by now, the official 64-bit RISC-V toolchain. In particular, it runs on their official Spike emulator, right? And their PK kernel. This was a major effort to get this done, but this is important because that means that we can actually execute it on something real and not just within our own emulator. There's a few more things here. There's an in-memory linker in there. There's a disassembler, right? So that you can actually read the machine code that comes out of it. There's a debugger, right, with rollback. I'll talk about this later. There's a profiler that tells you, gives you quantitative information about execution. How many times was the, what's the procedure that was invoked the most, and where did you do the most loop iterations, etc. This is very important for students to teach, optimization and things like this. It's very important to give students quantitative ideas of what's going on. And then there is an ELF bootloader. So we are actually, what we do is we reverse engineer sort of a minimal ELF file format for our system. We generate that and made sure that it runs on the official tool chain, but it also needs to be loaded by our own system to be able to execute it, right? So everything is, because of this self-containment, etc., everything has to be done very carefully. On top of it, the code is written in such a way that you can actually read it, and you're supposed to read it as a student, right? So there's no shift, no bitwise shift operators in the original language here. So you'll need library functions to do bitwise shifting, and you do this by multiplication and division, of course, using unsigned arithmetic, and students learn that, and then in assignments they're supposed to replace this with compiler support for actual bitwise shifting and so on. This thing here is actually getting a lot of attention, and I'm really surprised about it. It gets more attention than all the research papers I did before. Teaching is great, right? It leads to new ideas sometimes. There's a website, there's code, there's slides. We are working, there will be a new batch of about 200 slides on the operating system soon. And so I was told you have to do this if you want people to use this in class, you'll have to provide everything. And I think it's not enough to do just the slides, we also have to provide homework assignments. So we are actually working on an automatic grader for this system, and I will be talking about this tomorrow. And I'm working on a book as well. So, just to give you an idea how the code looks like, okay? So, and sometimes I get asked, why did you use this, ancient C, basic C language as the foundation of your system? And the answer is very simple. I did that because that's how I grew up, right? So I know this. And I'm sure you can also do this in different languages. But we did it in this one, and it was actually a challenge to get to this particular subset of C. This is also a contribution of this project, to know what you need and what you don't need, okay? So this shows you a basic function that probably all of you know. ASCII to integer, it takes a string of decimal digits in this case, right, as input, and then it produces the numerical value represented by this string of decimal digits, okay? And you can see that this is decimal because it computes base 10, recurrence relation to base 10, right? So this is beautiful, very simple. And it shows almost all features of the language, right? So there's only 5 statements here. Assignment, while, if, return, and procedures. In particular, procedure invocation as a statement, right? And this is very important here now. There's no data types other than unsigned integers, 64-bit integers, and pointers to unsigned integers, which are also 64-bit, because our system is 64-bit, everything is 64-bit. This used to be different. We had signed integers in the past, and this was a nightmare as we decided to move towards verification, because verifying stuff with signed integers is so much more difficult than if you just have everything unsigned. So we kicked them out, and the code became actually cleaner than before, which is an interesting insight. You only need very few places of signed integer arithmetic that you then have to put in the library to use it, right? So you have to implement a signed less than in the library, for example, if you don't have signed arithmetic. And then there is the dereferencing operator, this unary star operator of C, right? That allows you, given any number, give me the content of the memory address that's right there, right? Or store something in there, right? I mean, this is the nightmare of managed languages, of course, as we all know. But I love this stuff because that allows me to do everything in a very simple fashion. Okay, so it's right there. And what's important is that it leads to two different kinds of arithmetics, right? Integer, unsigned integer is this one here, and this plus sign is pointer arithmetic, of course, and has different semantics. And this is one of the things that the civil engineers really don't like. Like, why are these crazy computer science people doing that? Why would you overload something like this that everyone has at least an intuitive understanding of? You're not actually, changing the semantics from mathematics to this one here, but then you're also overloading it with something that has a completely crazy semantics, right? So this is what leads to confusion with engineers, and you need to actually explain to them. And you will be surprised, to actually explain where the semantics of this thing comes from. You have to lay out the whole damn thing. Memory, byte-aligned memory, words, byte addressed, word aligned, etc., etc. Okay? There's character literals, string literals in there. Those I didn't want in originally, but I had to put them in because otherwise the code is completely unreadable. Okay, no bitwise operators, no Boolean operators. This is all for you to do. Yes?
Why not using the square brackets like for array access? Then you wouldn't have to overload for the plus.
Because the students need something to do, right? So that's a beautiful homework assignment, right? And you do it in 1 week. You do a single dimension thing, and then they feel comfortable, and then you say, let's do multi-dimension stuff, and then it gets a little more interesting. So that's actually the reason. Yeah. Okay. This is important here. So the library boots the whole thing. Yeah. Bootstraps from exit malloc. Right. Nobody needs free, of course. Open, read, and write. Nobody needs close. Right. We have other people to clean up for us. Right. And if you want it, you can implement it. Right. Of course. Yeah. No, you see this malloc thing. Many students, especially non-CS students, don't understand malloc and don't understand how simple, on a logical level, how simple it actually is. It just returns a number, right? With certain properties, of course. But people don't understand this. People believe there's all kinds of things happening and so on. This is even for computers, young computer science students. This is an enormous insight once they understand the difference between a malloc call and what the operating system actually does, etc. Okay. So what we are doing is we are constructing a minimally complex, maximally self-contained system, right? And we are not so much talking about programming languages versus systems engineering, all that stuff. So I'm more in systems engineering actually, because you could do the whole thing in a different language and so on. But I'm not trying to do that. You'll see that there's lots of content that has nothing to do with the language. Yeah? Okay, let's go through a quick series of slides that show you how you actually use this thing. Okay, so first of all, you do make, right? And this will bootstrap the whole system, selfie.c, into an executable that runs on, let's say, your x86 machine. Okay. Now, if you actually invoke this, you'll get the usage pattern, which is kind of complicated. I'll just go through the features that we need for the talk. So you can, with this, you can compile any number of C source files, C star, in fact, of course, only, right? And then it compiles all of them and links them in memory, right? Then you can actually tell the system explicitly to generate a binary into a file that will be RISC-V compatible. You can also, and this is the new thing now here, or let's say something unique, is that you can, at the same time, after you're done with that, you can actually create an instance of a RISC-U machine, right, that is able to execute this code here with a certain number of megabytes of memory, and then it will execute this code right away. It can even compile code and then execute it like that. And you'll see this in a moment. There's also this -y option here that will actually launch the hypervisor rather than the emulator. Okay, so what we are doing now is we'll compile Selfie now, of course, right, with the Selfie binary that we just generated. That's the first thing we want to do. And this is how you do it. Okay? Very simple. -c selfie.c. Now what you get here is a lot of quantitative information. This is important for the students. So they have an idea, what are they dealing with here, right? So you can see that 40% of your code is actually just white space and comments and stuff, right? Almost 60% is actual code, and then you have these global variables and all the things that are in there, right? So this is what it takes to implement the whole system right now. Yeah. Then it tells you also how many bytes it actually generated, in particular how many machine instructions to do this, and the data segment, the size of the data segment. It also tells you, and this is now the RISC-U instruction set. It's only 14 instructions that we use. Basically just unsigned arithmetic, right? That's it. And it tells you, you know, how many instructions of what type you got in your executable.
Christoph?
Yes.
You didn't use comma when you declared the 3 local variables and A to I, and you're very conscious about the 10,000 line limit, and that would save you like 10% of the lines of that on A to I.
I know, and I keep, so here's the thing, I want to keep it at 10,000 lines, so every time I want to do something new, I have to do something like that first, and that's what we are actually doing, and but it's important that the code doesn't get, that the compiler doesn't get too complicated, right? Because I have to teach the whole thing.
So you're at that oscillation. Right?
Yes, yes, it's a whole oscillation thing right now, yeah. Okay, so this takes seconds, right, to do that, to just compile the whole thing, yeah? What we actually want to do is we want to compile Selfie with Selfie, right, into an executable, but then we also want to execute that executable to compile Selfie again. That's what compiling people do, right? We can do this in a single invocation of the system, okay? So we compile Selfie, then we create an instance of a RISC-U machine with 3 megabytes of memory, and that will get the rest of the console arguments. To that thing, it will just look like a -c selfie.c invocation, okay? Now this here gives us more information because now we are executing a RISC-U code on our emulator. So we know things about memory, how much memory did we actually allocate, and we actually know many other things like how many times did we execute any of these instructions relative to each other. We have a full profile of everything, yeah? And we even have a higher level profile that tells us about, you know, procedure call invocations, which procedure was executed the most, right? And the loops, which one was the most executed loop, and then the second most, and so on, okay? This requires you to implement fixed point arithmetic, which is an unbelievable nightmare. And I just did whatever I had to do to get this working. Takes a minute on the machine. So we're going from seconds to minutes, okay? Because now we are interpreting a RISC-U file, okay? What we actually want to do, of course, is we want to generate a binary out of the first one and give it a name and put it in a file. And we want to generate a binary from the second one and give it a different name. And then we do a diff on the two, and they are bit equivalent. Right? That's it. That's what we want. And you can do this with this kind of invocation, and then you do a diff afterwards, and you're done. You can see this in the make file of Selfie, how we actually do this. And here, beautifully, same number of bytes, everything equivalent. Now, let's move from compiler stuff to operating system stuff, right? And this, you see, this is important because teaching compilers is fun. It's beautiful. You have all these books and you have all this theory. It's unbelievable. I really enjoy teaching compilers, yeah? But then I have to teach operating systems. And that's a nightmare, you know, because you have the same, you want the same standards, right, in teaching. But then it's impossible because operating systems, you can either do a blah blah class and you stay on the superficial level, or you have to go in there and then it's an absolute nightmare to get anything done, right? So there's all these systems out there that you can use. It's unbelievably complicated. So I was always trying to find a sweet spot of teaching both, ideally, eventually at the same level of thoroughness. And, okay, so what we are doing now is the following thing. I compile Selfie with itself, yeah, and then I create an instance that's a little bigger, 6 megabytes, compile Selfie again, and then I create on top of that another instance with just 3 megabytes because that's what I need to do it here, right? I need 3 megabytes to compile Selfie and then another 3 to actually host the whole thing within Selfie. So now I'm executing an emulator on an emulator to do the whole thing. You can also do the fixed point check if you want. All that will go through, right? This takes hours, okay? So there's an exponential in the number of emulators, right? When you think about it. For each instruction, you need 1,000 instructions to do it, okay? So why would you ever do that, right? And
because you can.
No, no. I thought in the beginning, and it's unbelievably cool, and it actually works, right? But what it allows you to do is to teach operating systems, to bootstrap operating systems in a very elegant way. Because what you need to do is you should think of this emulator here, the first one, as your hardware. Okay, so this is your processor. And the second one is your operating system kernel that can only execute one process. Okay, and it can only do so through interpretation of code, and that's why it's super slow. Okay. Now the only question is, how do you get rid of this interpretation? And operating systems, what they do is, they take this code and instead of interpreting the process code, they ask the interpreter on which they run to execute it for them, using something called context switching and memory isolation through virtual memory, etc., etc. Very complicated stuff. But if you just do interpretation, it's like that. Take a, re-implement Linux, just do interpretation, and it will be vastly simpler than the real thing, and would actually be an interesting exercise to see if you can make a bit equivalent, right, the interpretation and the actual thing, and then do reasoning about its correctness. This is actually what people do with microkernels these days. In Selfie, we can do this. So instead of using an emulator here, we'll use our hipster hypervisor, which actually does exactly that. Right? It takes the code and asks this guy to execute it. And the effect of this, that we are back from hours to 2 minutes, because we are doing two-time compilation of Selfie. Okay? Now I'm going to talk, the rest of the talk is about how this actually works and some insight that we gain into that. Okay. So first of all, you can do crazy things with this, right? And I already mentioned this. You can have an emulator here and then a hypervisor. You can run another hypervisor on top of it. And then the compiler. All these things work as long as you have enough time and space, of course. Yeah? The compiler part of it looks like this, right? So we have beautiful scanner parser code generator. It's all very simple, recursive descent, single pass. Source code goes in here, and then it generates our code, in particular library code, in the correct format, so it actually runs on not just our emulator, but also on the tool chain for RISC-V. Okay. What's important is that the thing that the compiler needs is an open call. It needs to open the file that it's supposed to compile. It needs to read from it. It needs to open a file to write to, right, and then write to it. It needs to allocate memory. It never needs to free any memory, of course, obviously, if you have enough. And then you finally call exit, right? So the thing is, of course, that these 5 procedure calls, in essence, right, to the language, they look like procedure calls. For those, we have to generate wrapper code that wraps around the actual system calls that are then executed by the emulator and the kernel. And it needs to work for both worlds here, right? So that's what's happening. So let me show you some interesting, the cycles that are in here. First for functional code, not for the I/O code. So if you actually compile this piece of code with the system, right, then this plus sign is C code for unsigned 64-bit integer addition, right? The compiler will generate a bit of RISC code. In particular, this one, it will generate this instruction to implement that operator, right? An add instruction in RISC-V code. Now, we also need to implement, of course, the interpretation of that code in the emulator, right? And this is on the next slide. So this procedure implements exactly this instruction, but then in turn uses that operator again, of course, right? So now you have this apparent cycle, and you have at least 50% of the audience lost, especially when we are talking to students, right? And then the rest of the time in the semester you spend on telling them how you actually bootstrap on this. Of course, eventually this here is implemented by an x86 instruction, because that's the compiler that we use for bootstrapping does that. But yeah, okay. So the thing is that in this system you have to do both. You have to implement the compiler that generates the code for this operator, but then you also have to implement the actual operator. There's other things where the synergy becomes important. So for example, the code for encoding, correctly encoding these RISC instructions into 32-bit binaries, yeah, is done here. But then you have an emulator that takes code, fetches code from memory, and then decodes it. So it has to do the opposite operation. And of course, we have implemented that next to the encoding logic. So if there's any changes or anything, or if you want to understand both ways, you just look at the code and it's next to each other. So this is the back end of the compiler next to the front end of the emulator. Okay? There's synergy that even goes across compiler, emulator, and hypervisor. Okay? So for example, how do you implement an exit call, right? So there's compiler support to do that. You have to generate wrapper code that prepares a system call that will actually do the exit, which is this E call down here. We call it environment call now. So just think of it as a system call. But you have to prepare first the registers according to the convention of the PK kernel and the Spike emulator. Otherwise it won't work, right? So this is a compiler backend part. Whereas the implementation of exit you also have to do, of course. Since we have an emulator, it has to do that. And this code is right here. Yeah? And most importantly, this code not only works in the emulator, it also works in the hypervisor. Right? Which really makes it twisted, let's say. This is another example for the open call. It's a little bit more interesting, it's more complicated. We have 3 arguments here, we'll have to take them off the stack, and then we invoke the system call to do that, and the actual implementation of the system call for open is here, and then you can see how the code actually takes the arguments from the registers of the processor and then does the open call, which again is similar to the plus versus add thing. This one here eventually translates to an open call that is compiled by the GCC compiler into your binary. So it's interesting that GCC, without any includes, if you just use exit, malloc, open, read, write, will actually provide the code necessary for doing that. No linking required. I didn't know that before I started the project. Okay. Okay, let's skip this. This is malloc. Malloc is slightly more complicated to do. So here's this picture. Yeah, you have one emulator. This is our hardware, and that guy executes another emulator, which is supposed to be our operating system's kernel. And what these things do is they manage a context, let's call it a context, and each context of the machine is basically the registers and the program counter and 4 gigabytes of virtual memory. We actually implemented virtual memory instead. Yeah? But only the basic parts, only the mechanics. And then it's actually on-demand paged to physical memory. This is a detail that is not really necessary. You can actually do the whole thing with segmented, super simple memory, but then you have to make sure that the contained emulator always uses strictly less memory than the containing emulator. Right? So here this is not necessary actually. So when you look at the emulator, what it does is it executes these instructions, right? And every time it executes an instruction, it changes the context in a tiny little place. And you can actually have Selfie show this on the console. Every instruction leads to a tiny little change in the program state, in the machine state. Yeah? Now, there's also this notion of exception, and this is important in this whole game here. For example, if you do a division by 0, right, then there will be an exception, and now you have to deal with it. And there's basically two fundamental ways of doing that. Either the emulator, invokes some other code, operating system code, to actually do it, or it has to do it itself. And we actually implemented it in such a way which is not realistic, that the emulator does it. So our exception handling is part of the hardware, but it's implemented in a way that it can also execute on top of the emulator. I don't have enough time to go through this, but there's many other exceptions here. Page faults, timer interrupts. And in particular, if you execute a system call such as these, right, then there will also be an exception that deals with it. And both have to be done in such a way that it works on the Selfie emulator and the other system. Okay. Now, when we go back to this picture, what I ask students to do in a 1-week homework assignment, yeah, is to implement now an operating system that can execute 2 processes, alternating between the 2. This can be done in 1 week. Okay. It's very simple. You just hack this emulator to create 2 contexts, and then you do an interpretation of 1,000 instructions here, and then you go to this one and do 1,000 there. They're completely isolated, because interpretation gives you all of that, right? You are creating a notion of machine here, not using the machine on which you run, which makes everything simpler, right? And performance is, of course, a different story. Now, yes, the thing is that systems people don't want to do this because it's all about performance. So you really have to throw it out the door to get an idea like this.
Just a quick question. So when you have those 2 contexts, the way you do, preemptive multitasking is run context 1 for 1,000 cycles and then jump to the context 2, right?
Yes.
So the emulator keeps, the emulator is the one who's doing the timer, is the timer interrupt, so to speak.
Yes, absolutely, yeah. Yes, it's part of it. But this is not the issue here, right? The issue is how do we get to this thing where you actually have an operating system kernel that switches between these 2 contexts, but it does so by using this to execute it, right? And this is actually what works in Selfie, right? I don't have enough time to actually explain exactly the details here, but we can just flip a switch and go to this point. And then we also have concurrency here. Exception handling is now more complicated because this thing is not getting the exceptions, right? This thing down here is getting the exceptions because that's what executing the code.
Sorry, I might have misunderstood. Do you get them to manage the stack and program counter 2 explicitly as they do the switch between the 2 processes?
It's the emulator that does everything, right?
So the
code
students don't see the stack management when they do all of this.
Okay. So I'm running out of time. Let me skip through this here and just point out a few other things. So what's actually happening when you have the machine execute everything and the kernel is just running on top in its own context and then it's managing other contexts here is that the machine is really just executing everything. It's also getting the exceptions. And now you have to make a decision. Is the emulator going to deal with some of the exceptions itself, which is happening for this context here, but not for these, right? If these create exceptions, then they are relayed back to the hypervisor, and then that guy actually needs to deal with exit and open and read and write. But eventually it will all end up in this emulator. Okay. Now what's important in this whole thing is that this is designed, or it's done in a way that you can even alternate between interpretation and virtualization. Okay? So I can do 1,000 instructions by interpreting them. And then I can, the same context after the 1,000 instructions, now I can do a context switch and ask the machine on which I run to do the interpretation. So we have done it in a way that is even that clean. And actually supporting that feature made the code simpler rather than more complicated. Okay. Now, if you want hierarchy, if you want multiple virtual machines on top of each other, you need one thing to make this happen, and this is you have to implement this decision. You have to understand at this level here, where did the exception come from which context, and who actually created that context, because that's the guy who's in charge of handling the exception. Okay. So if there's an exception here created by this guy, then the emulator needs to know that it is supposed to deliver that exception to that hypervisor and not to that one, right? So you need this kind of information. This leads to a tree of context, essentially. That's the only thing you need for hierarchy as far as I see it. Yeah? Okay. There's more about the actual teaching experience tomorrow. Do some advertisement here. So the last few slides I have is on minimal symbolic execution. And yeah, so this has been going on for a year, and we are far from actually finishing anything. Even though we have only 14 instructions, yeah, 14 instructions to make symbolic, it's unbelievably, I mean, it's really difficult, but it's extremely interesting to look at your instruction set from that point of view, okay? From that, I mean, the ideal is that for people who are not really familiar with this, so what you want is that all your instructions now, they do not operate on concrete values anymore, right? There is in each register and in each memory location, there is a whole range of values in there, right? And now you have to redefine the semantics of your machine based on that regions or whatever you want to call it, or different sets of values, right? As opposed to a concrete value. Right? And this is actually very interesting. Usually what people do is you have two choices, right? You can integrate this with a standard SMT solver, and there's plenty of those, and they're very good, and there's people, really strong groups doing that, right? And I actually have a student working on that. So we just we play with Boolector, for example, from this, which is really a cool thing. And the other choice is that you do it yourself, right? As according to the spirits of this project, we have to do that in order to maintain self-containment. But that actually turns out to be a real nightmare. And of course, you can't do a full SMT solver in 10,000 lines, so you have to do some other things. What we actually do right now in this direction is that we try to create a reasoning engine that is based on numerical integer intervals rather than a full SMT solver, right? And we are playing this game of completeness versus performance. I'll say, if I have more time, 5 more minutes, I'll say a few words about that. But before I go there, I'd like to point out that there is an interesting connection. Before we get to the symbolic execution engine, there's a connection with the replay part of Selfie. Okay, so Selfie has this capability of executing RISC-U code and remembering, let's say, the last 100 instructions. Okay, now once you hit a division by 0, let's say, yeah, you can actually now make the machine roll back the changes created by these 100 instructions, right? And then you execute once more forward into the division by 0. But this time with output, full output turned on, and you can see what's happening. Where am I actually coming from? Right? This is what I mean by replay here. Right? So we implemented this, and so it rolls back n instructions. And this is interesting because in the code you actually have to say not only what you saw before, the do semantics, add 2 registers. Now you have to do the undo semantics, of course, which is another thing that's very sort of that creates a high effect with students, that such a thing is even possible, that the machine is so deterministic that you can actually do this. Of course, this is not fully true because system calls, how do you undo a system call? It's a lot more complicated. How do you undo writing to a file, all this stuff, right? So we have done some things there to actually make it work, but that is not a complete solution. Okay, then we re-execute and print on the console, and we use a cyclic buffer for replaying n instructions, and that buffer is the one that we are also using in the symbolic execution engine now. Now the symbolic execution engine actually needs to have a buffer that is as long as the deepest branch that you are exploring, right? But it is otherwise just like a replay buffer, right? What we'll do here is we fuzz the input read from files, so any character that you read is now, could be anything from 0 to 255, right? And you have to store that information, and then it propagates to memory and your it's completely symbolic. Yeah? We proceed right now by computing integer intervals, which is much simpler than generating a full SMT formula, right? With all the machinery that you need to reason about it. And the good thing here is that we only need to record memory stores, right? Not even register stores, not even modifications of registers. So you can really focus on this, and ideally you would get an engine that is linear in the number of instructions that it is executed, right? And not whatever it is, you know, when you use an SMT solver. However, you typically lose completeness very quickly, which means you are exploring branches that are actually not feasible anymore, for which there is no input anymore. So this could result in false positives. So you have to get rid of this. So there is a trade-off here between essentially identifying a subset of programs on which you can still do this in a complete fashion. And some of the spirit of this project is that we believe that there is interesting kind of systems code for which simpler engines like this are still complete. Okay, so this is the vision that we are following here. Okay, in Selfie, the compiler falls into that subset. So far, we're always playing this game. Sometimes it does not, and then we have to expand the engine, make it smarter, make it more complete without using a full SMT solver. And we can detect division by zero, unsafe memory access so far. There's more things that we'll have to do, witness generation. Like in a system like this, if you hit symbolically a division by zero, then you can generate an input file that when you feed it concretely to this code, it will run exactly to this division by zero, which you could validate in MIPSTAR right away. Loop termination is a difficult problem. Parallelization, we have a parallel version of Selfie, which is surprisingly easy to do. For symbolic execution, you can basically utilize any parallel machine you want, but it beautifully parallelizes. And of course, it also occupies all the memory that you ever have, so you have to be able to address that as well. Right, so that's it. If you have ideas about this, we are glad to help get you into this. This is a realistic sandbox that allows you to control everything, and it's fun. Sometimes if you want to just play with a feature, it's usually just a bit of code that you have to do here and there, and then you can play with that. And that's all I have to say. Thank you.
It's a very interesting talk. So, are you using the symbolic execution to basically debug code, and in particular Selfie?
So originally the idea was to do some verification stuff, to add it, like let's say the grand scheme is to be able to teach formal methods and verification to bachelor students. Okay, so this is what I would like to do, rather than keep this a master's class. Okay. And so I thought about, can I actually get some sort of verification into the system? And then I saw there's symbolic execution, which is not verification, but it is at least something that approaches more systematic ways of showing correctness. So that was my original goal. Now I think the research part of this project is to study ways of simplifying execution engines, making them incomplete, but at the same time fundamentally faster, right? And then show that you can still reason about interesting kinds of code. So that's the problem that we are studying.
Okay, so I just want to point out that in your A2I function, you have a few bugs.
Oh, of course. What you saw here doesn't actually work at all. Look at the code. Look at the code in GitHub. It's different, right? But I'm sure there's also bugs in it.
From teaching perspective, the lessons the students learn in here, can they all translate safely into C and C++ when they grow up? Or how do you make sure that they don't need to unlearn some of the things they learn in this? Sorry.
So, no, this is a good question. So my experience is in the beginning, I always have this problem that I have to unlearn some of the things they learned before. I'm not sure about what happens after. Usually I get asked, can you actually make more students graduate successfully? I don't think that's actually true. It's actually polarizing, I think, some of it. But I think you can make the good students better. That's the kind of experience. What they then have to unlearn, I'm not sure. This language here is so simple that I don't know. To me, most students that like the class, they come to me and then they say things like, finally I understand how the damn kernel works or something. So, yes.
With students, how do you browse code? Do you use some special tool or just hyperlink version? How? Because I imagine one large file is hard to...
So I'm this non-GUI type, right? So I tell the students, please throw away your GUI, and for this class you need a terminal and a good ASCII editor, and a compiler, and that's it. And then if you have a really nice editor like Sublime or Atom or something, and you know how to use this, then you can beautifully browse the code and so on. So that's what I usually do. But there's students who just can't. Right? So this is actually maybe a generational issue, or I don't know what. But I think it's some students, they look at me and think probably that I'm already mad or something when I go through the source code and even explain what the semicolon in C source code, what its purpose is, or its original idea, what the compiler does with it, etc. So that kind of focus is something that many students are not used to anymore, right? And because of all this GUI stuff also that distracts you. And that's why I'm saying just use a terminal, which is like a chat, right? It's the chat with the machine or something. So it's immediately cooler, I don't know.
You just need to put every instruction in a little bubble.
Yes. Yeah, that would be really nice.
That's the other side of the screen is the output.
But then we have all the time to actually just focus on every single detail of the system, right? So I hope you saw that this thing requires you to understand essentially everything.
Yeah, uploading consciousness will be necessary to keep these systems working, right?
I don't know.
Yes, for the exercises, do students get access to the full implementation, or do you have like incremental versions?
Yeah, I completely gave up on hiding stuff, because they can share everything, and so this is all public. You hear about it tomorrow if you want to go to /E. We are working on something that we call a self-grader, obviously. So the idea is we'll give students, in fact, Python scripts. Sorry about that, but these are scripts that they invoke, and the script tells you, based on whatever code they did, what the grade would be if they submit now. So that's the idea of the talk tomorrow, at least part of it. Self-grading, which I had to do. It was just so, with this kind of theme that I have here in here, it was just so close to actually do that. So that's what we are trying to do right now. Yeah. Yes.
So why is it C* after all?
See, I forgot to mention this. It's because of the unary dereference operator in the language, right? Since that thing is so important, it's the only way to access dynamically allocated memory on the heap. I mean, it's a way to access any memory. That's a different story. But in particular, the memory that you allocated with malloc, and it's the only way, right? So there's no brackets, there's no arrows, dots, no structs. And students come to me and they complain and say things like, but I want to use my structs and so on. And then I say, sure, you can use structs, but you first have to implement them. And here's the assignment. And that's actually what they do.
So they effectively have to implement padding by themselves, iterating through cars by themselves.
All these things, sure. Absolutely. But it's easy.
I mean, as an alternative, wouldn't it be also possible to just, throw them a fourth implementation and let them hack with it?
No, I think an important issue is these days is that you want something that is self-contained. This is very important because I believe that many students feel lost. There's so much information there. Like when I took all these classes 30 years ago, it was completely different, right? Even then there was already a lot of material, but it was way simpler than what's going on today. So I think this is one of the key values of this project is that you take it, you have one file, and you just study that. And it will give you answers to everything because it has to answer everything in there. So, and not, all these other things.
So this is very reminiscent of Dan Ingles' claim that you want self-mastery, that the system should be simple enough that one brain could actually comprehend everything in it.
Yes, and for teaching this is certainly true, but even I would say for some things you do in research, because we just want to study this one thing and not, anything else. Yeah.
Do you teach everything in one course, bachelor level, or just the compiler bachelor level, and then you go on?
No, I need 3 classes to do the whole thing, so it's 1.5 years.
But is it master students then or bachelor students?
Both. So it's a bachelor compiler and then operating systems, and then there's also a master's class. You can take this and do really fancy lock-free stuff, atomic instructions. Like you want to do a lock-free Michael Scott Q or something. You implement this, but before you can do this, you have to implement compare and swap operators in the emulator and so on. So yeah.
And what's the bachelor level content? What's the bachelor level content of the course?
This is compiler. First of all, it's very important, right? First, we have to get the compiler out of the way because otherwise they don't understand memory layout, right? Stack, heap, code segment, all that stuff. Where is this? What's the program break? All these things. The compiler class will teach you all of that, and in particular how you get from high-level semantics to this low-level code. And then the operating systems class 1 semester later tells you all the things about the runtime system, about the emulator, the kernel, in particular virtual memory that you didn't see today. There's a whole on-demand virtual memory paging system in there.
But how do you deal with students? I don't know. When I teach classes in bachelor level, 99% of the students have Windows operating systems. So getting them to something on Linux, like to explain stuff in a non-proprietary way, it's not actually easy because they don't know how to handle the operating system in the first place in the 5th semester.
Right. But they only need a terminal, right? So even for Windows, you can have a terminal, right? And then you just, and a C compiler. That's what they have to do. I tell them, of course, how to do it if they don't know.
But you work in a Linux subsystem then, or what?
I work on a Mac, but...
No, but like the students, for the virtual memory stuff, I guess you design everything around ELF and to be also executable in x86.
No. That's a misunderstanding. So this does not, the code that we generate runs on a RISC-V toolchain, not an x86 toolchain. I have one student working on that, a binary translator, to make this happen, but this is a totally different kind of thing. Yeah, so we are not producing x86 code, not yet. Right? We are trying to do that, but yeah, this is of course interesting to do. But of course, but the code is written in such a way that it bootstraps on Mac OS, on Linux, and on Windows. Okay, without using any kind of configuration flags. Look at the code, the Selfie code. Where's the problem when you want support on all these 3 different systems? The problem is in the flags for the open read and write calls. Okay? And we found a combination of flags that works on all 3 systems.
Okay, one last question. Well, then let's thank Christoph.